Okay. Hello. Okay. This is all very boring. Why? There he goes. Okay. Hello, folks. I have a city tree cutting crew across the street taking down an old tree. So we will see how the sound quality goes. I'm giving folks a few minutes to show up here. And chat says, barely noticeable. Okay, good. Yeah, well, they're better right now. For the last hour, they've been doing big things with big chainsaws, but I think they're down to cleaning up. Hope everyone had a good week. I've a good 2 weeks. I've had a really nice trip here.
Where did you go?
Yeah, I was giving folks a few more minutes to show up, and then I do like the 10 seconds of, hey, you know, you're being recorded, and then the usual, like I don't have an agenda other than to, you know, get my hair cut right now. Still no hair places open, and it's just like, it's like, I guess I should be happy I have hair, but it's driving me nuts.
Yeah, me too. I went through it with a clipper last Saturday, so now I'm completely short.
Right. That's coming shortly, where my wife is going to try to clip my hair, and then I won't be presentable on, you know, Zoom for a week.
Wear a hat, maybe.
Yeah. Well, it's officially 10. Oh, here's some more folks. They always show up in the last couple of minutes. Yeah, okay, so, you know, I'll do the spiel once, maybe do it again here in a second. So, this is Coffee Compiler Club. We're here to talk about compilers and language runtimes and whatever. I don't have any set agenda. I do record these things and put the link online later. So, and I'm typing because I'm also tracking who's showing up so that I can just keep it sane here. I tried once and had no filtering and had huge spam bot attacks with Pornhub. It was very, very exciting, but not compilers. You're live, you're being recorded. I'll put the link up an hour later or whatever, however fast Zoom gets around doing links. They got behind for a while. They seem to have caught up now. I have no set agenda. I run an open mic policy. Just pop your mute and say something. I'll moderate if necessary. It's not been necessary. It's all good. And in the last several go rounds, we've sort of beat to death like how to do interface calls, what the problem is with interface calls and hot inner loops. And we have a fellow who's attempting to join and failing. I'll give him another shot here. Nulls and what they mean and what's the life in the universe of nulls and why we care. And like I said, I don't have any other agenda. Here's a couple more.
While you're doing that, I'll just say hello, Cliff.
Hello.
Good to see you. Back from your road trip, I guess. Yeah.
Well, here's Cameron too. Okay, people piling in fast now. It was sad state of affairs. Just my mother's 85 and starting to lose her memory, and that's just what happens. So I went to go see her, and I had planned to go, start of the year. Well, it was cool. My wife and I like to drive. We were going to do a nice driving vacation. That got put on hold for 3 months. We decided to go anyhow at some point. So yeah, we drove. We drove through Joshua Tree National Forest and camped. It was really pretty. I've never done that before. It's a really fantastic place.
Beautiful.
Drove to Tucson to see my stepmother, who's also 85, but in really good shape. Drove to Houston, which is a 2 full day drive from Tucson. This is not a short drive. Visited my mom, visited my sister, went to the museum, we tried to go to Brazos Bend Park, which has alligators, but they were full, both of alligators and people, and they were socially whatever, so couldn't do that. I don't know, we did a bunch of other stuff. Then visited a high school buddy that I'm still kind of in fairly regular contact with. And we just talked, 40 years of history, like what the hell happened to our lives in the last 40 years. And we camped out on his farm, his ranch, basically in the prairie, put a big fire pit out and, drank beer and under the open stars on the prairie on a warm evening with the cows mooing in the background. It was sort of as classic as you can get. And then up across diagonal through Texas, which is not a short drive. And, Roswell to go see the aliens and standing on the corner in Winslow, Arizona. So did that. That was fun. Meteor crater, I don't know, ghost town, back yesterday afternoon.
That's great.
Still doing laundry.
Glad to hear that. For me,
Yeah,
going out it seems like you have to worry about encountering zombies along the way. I'm about to play Last of Us 2, which came out yesterday, which is about that. Like disease ravages the country and you've got to survive.
It's pretty close. Along the southern route, I'll say that at every little minor gas station and truck stop we went in, say 90% of the people were not wearing masks. And 10% of the proprietors were not wearing masks.
Oh boy.
Right. So we would wear our masks and, rush in and, use the restroom and pay gas and rush out. Right.
Yeah.
What you gonna do? Along the northern route back, it was a lot better. Most folks were wearing masks most of the time. And all of the sort of tourist trap roadside attractions, people were pretty good. They were a little more enforcement of things. The nicer restaurants had a thermometer, had a remote. They scanned your forehead. The tables were all spread apart, and all the staff were using masks, and everyone was polite about it. It was reasonable. But you wanted to get gas, long haul truckers would get out of their truck, you know, wander over to the bathroom, take a piss, grab whatever, snack, beer, whatever, and get back in their truck. And the locals were doing the same thing. And, you know, it was a small 5 and dime, and that was the major store in town. And there was a lot of sharing going on there. I don't know what the hell you do about it.
Yeah.
So it's the state of the U.S. and compliance with, you know, with the current virus affairs. Some better, some worse.
Shocking that the numbers are going up, huh?
Yeah, Arizona is taking a current spike. They're opening up more and they're spiking, and I totally get why. You know, having just walked across it or whatever, drove across it. Like I said, I don't know what to do. It was the southern route, it's along I-10. That was the issue. We came back across more or less I-40, and not really a problem. Everyone was being reasonable about it. So I'm in self-quarantine for 2 weeks. We'll see what happens, but I don't know. I don't want to say too much, but I rarely get the flu, and I do. It gets me for a day, so I'm probably going to bounce fine. See how my wife holds out. So here we are. I think we people quit showing up. So the usual 10 seconds here. I'm recording this. If you don't like that, you know, bail out. I'll put it on Zoom, up on Twitter, a link well, within an hour or two, whenever Zoom gets around post-processing the video. Open mic, say what you want to say. There's, I don't know, 15 people here, something like that. So mute yourself if you're not talking, because we'll have dogs barking, cars driving, and whatever. I myself have got city out front of my house, across the street, taking down an old large tree. They've just quit running the chainsaws continuously for the last hour. So it's better now, but for the last hour, it's been pretty freaking loud in the house from that. Compilers, language runtimes, garbage collection, type systems. I think we beat null to death. We beat interface calls to death. I'm ready for something new. Anyone can bring up any topic. I'm not trying to steer the conversation. Someone says
PLDI stuff this week.
PLDI. Well, throw out something from PLDI. That's all good. If you want to pile in. Like what's PLDI talking about this time around? I haven't looked at all.
It runs the gamut. I mean, they kind of had like 3 papers from every facet of the soccer ball. So everything from hardware verification to quantum compilers, which I know nothing about, to you know, slightly less inefficient parsers.
I thought parsing had been dead horse, but fine.
There was a pretty interesting keynote by Richard Jones on garbage collection. So he's written the famous garbage collection handbook, and the keynote was actually pretty interesting because he has pretty much given an overview of the research over multiple decades, but also including the recent one. And he had pretty interesting comments about verification, that he sees the value, it can certainly help, but it is also very much a lot of effort up front. So, but he also doesn't like debugging garbage collection algorithms for obvious reasons. So the somewhat in between approach is lightweight model checking that he has found worked pretty well for him, that it was not as much implementation effort, and he could do this incrementally while working on the garbage collection algorithm itself, and it caught some really nasty bugs. So that was an interesting takeaway from me, because I don't know that much about model checking in the context of garbage collection, mostly in the hardware and FPGAs before. So that was interesting to find out.
I've used model checking for state machine programming for my highly concurrent algorithms, but not for garbage. So I can see the use for garbage collection. Yeah.
Yeah. And I know from hardware, for example, for FPGAs, model checking is awesome. I mean, this is pretty much another world compared to test benches. So sometimes I wonder why isn't it as popular in software world, because for FPGAs, it can find really nasty bugs, and it can do it relatively quickly.
So I wrestled with this problem for quite a while because I worked with Azul for a decade, and that was, you know, here I am, a software guy, and there's a hardware team next to me, and they're like,
Right.
why the hell you guys don't do this? And the usual story comes back as something like, our problems are too complicated, and the cost of failure is a hell of a lot cheaper.
Right.
So you blow out exponentially, vastly faster than the hardware guys do. So you can't actually run a model checker in any length of time that's sensible. And the cost of failure is you get a crash in the debugger and you try again, as opposed to you wait 6 months while you turn around new silicon.
Right.
So there,
I think that's
Can
reasonable.
Can someone elaborate what you mean by model checking and specifically how it applies to GC?
okay, so model checking is a formal theorem proving, effectively. It's an enumeration of all possible states. So I run this thing called non-blocking hash map. It's a highly concurrent, linearly scaling hash map, fast, low, constant bounds for gets and puts, independent of readers and writers, which is sort of, you know, not sensible in any normal mechanism. And I do it with a big state machine. And then how many states are in the state machine? Well, not too many. So because there's not too many, I can model check it. And that means exhaustive enumeration of all states and all state transitions. So I had a grad student do this using one of the classic model checkers. I probably had a few, 100,000 states, so not too bad. For larger things, I've worked with Microsoft engineers on model checking device drivers. And there you would get hundreds of millions to billions of states. So you have to go check every state. So you have to have some sort of way to efficiently enumerate them, record that you've already visited them because you revisit the same state over and over again. So you have to hash them in some giant ass hash table that holds a billion elements, for instance. You want it to be concurrent or distributed or both. So for speed, because you're just doing this exhaustive enumeration. And then there's a state function that just, given a state, here's the next state, one of several transitions according to whatever it does. And you just list them all. And out of that comes like all these weird states that you didn't think about that leads you down these crash situations. Exactly what, this guy, the Richard Jones is looking for in GC. Suppose I have the GCs in this current state where I'm in the middle of rewriting pointers and moving from A to B, and the mutator changes this and this mutator changes that. I get a new state where somebody's in the gray space and somebody's in the black and somebody's in the white, and I move a gray pointer to a black pointer, whatever the hell. And then suddenly, I lose my invariant and I die. So model checkers will, because they do an exhaustive enumeration, will give you a counterexample, directly in your face. To do so, they enumerate all the exponential space. Well, that can get really big, really fast.
So essentially, you enumerate all the input space and then check your invariants, which you expect to hold for all inputs. Right,
and the sort of the nature of the algorithms you write is you're trying to avoid certain state spaces. So it's not an exhaustive enumeration of your inputs directly. It's given this inputs, I have only the following transitions are possible, and I get a new set of states. From those states, new transitions are possible, and you repeat ad infinitum. So it is not a for all loop for all inputs. It is given a state, and you start with some initial state. Here's the transitions, and now I have 5 choices. Each one, I do a transition of 5 choices, and rapidly you grow exponentially. But you get common states all the time, so the feeding branch of choices folds back in constantly, so you have to hash. And you often do things with reflection to get rid of mirror image shapes and the like, wherever dimensions you can do mirror image removals to cut down the count of states. But it's not a for all loop over inputs, but it's a general notion.
So for FPGAs, you often do either bounded model checking, which is pretty much what Cliff just said, and there's also inductive model checking. So the concurrency case is particularly nasty here, because imagine what you are designing on FPGA corresponds to something like a prototype of a modern superscalar out-of-order CPU. And you would like to verify that every single invariant about your pipeline is going to hold in your Verilog. implementation. So for example, while you are fetching instruction in one stage of the pipeline, you have to rely on that instruction having been present in the instruction cache, which is responsibility of the memory stage design of your FPGAs. And you also have to decode this instruction before you execute this, but you also don't want to have resource hazards. Basically, you have a very complicated concurrent state machine when a lot of components can combinatorially interact with a lot of other components, which is kind of, I guess, similar to concurrent garbage collections. And it's very easy to make an error. So what you do here is, for example, if you express those invariants that only fetch instructions that actually are present in the iCache, yada, 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 and you check that those invariants hold for initial n cycles of your execution. And this is the bounded module checking here corresponds to having a bound for those first n cycles. And oftentimes this is already enough to find some really non-trivial bugs to find that testing wouldn't really, I don't think that a human being would be able to come up with a test for that. Yeah.
Anytime you do concurrent algorithms, you get into the same kind of ridiculous scenarios where you'd never think of this one, but somehow if you look for the pattern, if somebody looks for all the patterns, they find it, they show you, oh, look, you did this, but you did this, and then somebody escaped this pointer outside of a lock, and this load bypassed this store because it wasn't volatile, and suddenly I get this value, and it cascades, and then sometime later you blow your invariant, you die. So it's expensive and useful, and you can do some amount of design work and software to pick algorithms that are easier to model check, which is probably what Richard Jones was talking about.
Also, I think that things like log-free algorithms and memory models, also if you are implementing a memory model in your compiler, this may be useful to verify the correctness of that, because that's another place when you have combinatorial explosion of non-trivially interacting states that are hard for human beings to track manually, basically.
Yeah, I've been down that path maybe twice, 3 times. So there's some model checking games for non-blocking, for lock-free algorithms, for several different lock-free algorithms. And then we didn't do model checking in the hotspot C2 JIT, but we came up with a set of rules that we agreed would pass. Somebody else, PhD, paid the price to decide that those rules would meet the Java memory model spec. Although they were more conservative than necessary, they were easy to implement as an engineer. So I implemented the Doug Lee Cookbook rules, which are not necessary, but they are sufficient.
Speaking of Doug Lee, he's on this afternoon, I believe, with an Ask Me Anything. So.
Oh yeah. Oh, nice. Okay.
The conference is free, so you can always jump in.
Oh, it's going to be online, of course. I didn't even think about that.
Oh yeah,
the PLDI in years.
The YouTube streams are pretty much all online, free and without registration. There's also a conference Slack, which has quite a lot of people, but that was registration only. It's pretty cool that they are making this available for free, I think.
All right, the link's in the chat. I might take a look at it after a while. I'm still unpacking, but it's getting better. We have more laundry to do and more dishes to wash and that sort of stuff. More mail to catch up on.
There was also a pretty interesting talk about patching x86 instruction code without control flow recovery. It relies on this technique called instruction panning. Basically, if you have an opcode in x86, you can encode it, and then imagine that you have a stream of bytes, which is basically your machine code, which is encoding of your assembly code, right? And the instruction panning basically notices that you can overlap the interpretations of instructions consecutive after each other so that you can interpret part of an instruction as another instruction. And what this allows you to do is you can patch, even if you want to have a single byte instruction that you want to patch out, notice that you cannot just do a jump to a trampoline, because the jump instruction, for example, you're going to have an opcode like E9, and then you're going to have 4 more bytes for a 32-bit address. So you would need to insert 5 bytes into your machine code. And without control flow knowledge, you will not even know if it's something that's on the boundary of a basic block that you could extend. But what you could do is you could change that one instruction. Let's say it was a pop. That's one pop RDX. That's one opcode, and then you have 4 more bytes. And if you are just lucky enough that those 4 bytes can be an address that you can jump to, then you can insert trampoline there. And that's just the beginning of that. That's pretty much because there's insane amount of engineering work to actually make it practical in more general cases other than this one simple example I talked about. And he practically covered most of those cases. So
wow.
that talk I highly recommend if you are interested in x86. And
I did the machine code generation, right? And so we had a bunch of self-patching pieces of code. And so across different architectures, including x86. And so we had to have patchable pieces of code, but those were all carefully engineered. They were not arbitrary patches. Like inline cache has it has a state, it's a cache, it can miss. It has a state that's empty. It's got a key and a value pair. The key and the value load, compare, and branch if it's okay, or fail if it's not. Or it's got a jump to a trampoline, which is a jump, load register kind of thing, load, jump register. A couple different modes. To patch those required that the 4-byte offset that he's talking about had to not cross a cache line boundary because you couldn't patch it on x86. But we would have a constant value, a jump target address, the type of the jump is a byte, and 1 or 2 other opcodes that we didn't let span cache line boundaries, and we stuck NOPs in as appropriate to avoid that. And then we use CAS instructions to do atomic patching in the iCache. And then we had to design to handle any processor seeing any partial patch because of the rules on the x86 are really loosey-goosey.
Oh, yeah.
So it was a pain in the neck to engineer, but we engineered for patching as opposed to trying to handle an arbitrary patch. The first version of SafePoints and Hotspot did the arbitrary patch with a 1-byte break instruction.
Oh, wow. That sounds cool.
Well, it's expensive because you take an interrupt and you inspect the return PC and you do a lookup to decide where you came from. And then you decide what you're doing next. So if you wanted to stop for a GC cycle, you stuck breakpoints down at GC points and you let the process run until it hit a breakpoint. And then you look to see where you hit. But you didn't patch all the code, it's too much. So you stopped a thread, you asked what function is in, you patched the function, and you started a thread, and you waited a little while. And if it stopped, you were good. And if it didn't stop, he got out of the function without hitting a breakpoint because that's just where he was in the execution. So you remove the breakpoints that were no good, and you stop the thread again, and you asked him again, and you put breakpoints down again, you let him go again. And after 3 or 4 go-arounds of this, you'd catch the thread. It's very expensive to save point threads.
So what's the so that's for a concurrent global shared garbage collection. What's the current?
No, it's for class loading too. Anytime you have to stop a thread for any reason, right, including class loading, right? So, any compiler deopt point, any compiler deopt event. There were a bunch of deopt events. Like you never ever made an object of this kind before. You loaded the class, you never made an object, right? Oh, you knew, now you made an object. So any load, which would known to have been nil before because you never had those objects, now might not be nil.
It's just that it seems like it's a perfectly valid approach when you've got a total of 2 cores and 7 threads, right?
Okay, fair enough. Fair enough.
I'm just curious if because
Azul flipped to a load compare branch. Right, and even on x86, it's essentially half a clock cycle because it's cache hitting load in a highly predicted branch, and therefore you just set the flag in the thread local storage memory, which is accessible off stack pointer. So you take the stack pointer, you do a little math on it, you load a bit, and you branch. It always predicts correctly. It's always an L1 cache hit. It takes half a clock cycle on x86. No patching, guaranteed hard stop every time. Much better answer.
Well, wouldn't you say, just looking at the direction that hardware has taken and so on, like when you have, say 4 CPUs, each with 128 hardware threads now, and that's well within the realm of $50,000. Like, so
I had the Azul box. I had 1,000 real threads. I mean, 1,000 real cores. But yeah, right. I totally get it. Yeah, you have to have something that doesn't involve. You have to have something that's more reliable.
Well, what I was going to say is you have to have something that doesn't involve getting everyone to stop at the same time, right?
Yeah, that was a different one. That was Azul only, not at Sun. At Sun, we still had the patch and continue, and that got replaced eventually. At Azul, we right away went to, test a bit and branch, but then we went to per thread stopping. And that was only, I don't know where Oracle's been at the last 20 years. At Azul, the first thing we did was put in per thread stopping. So a thread could be stopped basically within a short number of nanoseconds, a couple hundred nanoseconds. And that let us do a low latency GC where you would do a ragged safe point where every thread crossed a boundary, but they didn't all have to cross it at the same point in time. Right. That was the crucial trick that was, brought latencies down. There's latencies to safe point on the Oracle JVM had been running in the high millisecond range if some thread was playing bad, or if you had 100,000 runnable threads, you could be there easily. And Azul got it down to short nanoseconds for a thread and microseconds for thousands of threads by doing it this way. There was one other trick, which was whenever you decided you were going to take a thread off the core, the running core, you safe pointed it before it came off the core. So that if you had 100,000 times more runnable threads than cores, that at the time you need to do some sort of GC thing, 99.9% of them were already at a safe point, and just had to safe point the ones that were still running. So then you took all those already at a safe point, you did what you had to do, which was usually a GC thing, which was usually crawl their stack and flip their pointers. And if they hadn't been touched since the last GC time you did that, you had some fast cutout and said, yeah, 100,000, well, 99,000 of them didn't do anything, so I got no work, and 10,000 I got touched, and without anything stopping. And then I went to the 100 guys that were running, and I stopped them all and had them self-crawl their stack. So there's all these tricks to bring the latency down, but by large, you had to deal with that. You had to think about it. The first cut at Sun was just like, hey, this will work, and you walk away.
Jordan put a link in the chat.
Yeah, right. There's the Azul handshake is a whole lot cheaper and easier, but the handshake already makes the huge. Like I saw this come around some years ago. It's hugely better than what had been there before. The Azul version has, your stack is locked by you while you're running it. It's locked by GC while GC's crawling it and mutating it, and it's unlocked. And there's just a state bit that says it's locked or not, and it's usually thread local storage stack pointer value. So there's a funny things you don't think about until you get into these implementation games on GC. You stop a thread and call a stack. Well, it's expensive. If you have to ask the OS to stop a thread, you lose. It's not only unreliable, it's slower than hell. So you ask a thread to stop himself by setting a bit in his thread local storage. And in this case, you throw the bit down somewhere. I have to look at the exact details. I remember looking, it was a more complicated state machine than what Azul did, but it was morally equivalent.
I think for normal safe points, they also switched. Instead of doing break instructions, they test the pointer, and then to stop the thread, they just make the memory page inaccessible. So you go to the signal handler and you do what you want there for the safe point.
Yeah, I remember it was a big step up from the breakpoint. I saw that transition go by, and I looked at the cost. So we did the bit test instead, so you don't even take an exception. The usual story for stopping for a breakpoint, for a safe point, is the thread can do the self-service task itself. And it can do it a hell of a lot cheaper than anyone else because it's all hot in his L1 cache. So if you need to just record all fresh pointers that you've since the last whatever, if he tests a bit and he fails, he jumps to a handler. So it's a load, compare, branch, mispredicted cost, but I'm in a handler. The handler just says, walk my stack, which is hot in my L1, and throw some bits into a bucket I've got off to the side that GC will go collect later, and then go back and begin executing again. the cost of an exception throw for a failed read is actually the larger part of that. And that was sort of the common thing. The other really common one is I just had to have a mode flip. I just had to acknowledge that I passed a safe point since some GC, and I literally, the thread flips a bit saying, I hit a safe point, and he carries on. So there were a lot of safe point tasks. There was bias locking checks. There was stack crawls for GC, including partial half crawls because you only went so far, mode or phase flipping games. We eventually had like 15 self-service tasks a thread would do at Azul, most of which were super cheap compared to the cost of taking an exception. So instead of doing a load, which might fail, we did a load compare branch, because an x86, that's like fucking cheap. It's so, pardon my French, it's super cheap. Debug info validation. Oh, that's a good one.
Oh yeah, that was very, very interesting. So that was for the also C++ context, LLVM and GCCs. There's a lot of effects on optimization when you lose the debug information when you optimize code. And oftentimes it's very hard to do this well as a compiler developer because manually you have to keep track of everything. For example, the cases where he has shown this was dead code elimination. You'll, for example, have a bunch of trivial statements that you can trivially eliminate because you know that you are not going to use them in the computation, but it turns out that some of those statements were still useful because they only had attached debug information. And just because those statements were eliminated, when you run the code in the debugger and you are trying to follow what's going on in the code, you will jump between the lines or you will have missing values optimized for the function. So he has come up with a pretty interesting automatic way of testing this and seeing whether he drops the values or not. In compiler, this is known as differential testing, basically. And he has run this with the different optimization levels and compared the triples PLV, which was the program, an optimized program, location for the value that is going to need tracking for the information, and the value of what we are tracking. And that actually found quite a lot of bugs, both in LLVM and GCC. That was a very interesting paper. So
Hotspot went through this 20 years ago. So there's like a couple different things. This is like, this is good stuff. I'm kind of surprised it's still coming around. We had to have optimized code.
Permanent problem.
But we had to debug it. So it was Java came out with the first real debuggable optimized code. And that was the optimizer kept alive all the local variables that were visible at safe points. And you could stop at a safe point and then do stack inspection. If you wanted to modify, he would de-opt the stack and turn you into a interpreter frame. And now you're just single stepping in the interpreter until you rejitted.
I also know that many game developers in C++ actually prefer Visual Studio, and it could be because of that, because they often say that the debugging experience is much better in Visual C++. So chances are they are doing something that the other compilers aren't, but that's not open source. So
it's right. It's you want to have debugging. I totally agree. So the thing that Hotspot did to help with this debugging of optimized code, we had a set of flags we called blah 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 a lot, where blah 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 was codegen a lot, optimize a lot, safe point a lot, GC a lot. There were 20 of them, and they took all your slow paths and made them common. So if slow paths are common, you run super slow. So slow paths should be rare, and fast paths are common. But fast paths have all the optimized things and lose all the information. So you run the slow path in the testing harness over the weekend, and just test that you can access all the local variables that you can access or mutate or whatever the hell you're testing for. But we would have versions of flags that would force to look at. And I don't know what these guys were doing. It wasn't technical validation, but it definitely would check every possible point at which the program could be stopped that you could get at.
Yes. And they inserted unoptimizable code like calls to functions that don't exist just to prevent it from optimizing. I pasted one more paper, which I think you will appreciate, coming from JVM community. So you probably remember the self work and how they introduced the optimization. Yeah. So this paper does this for debugging C++ on runtime. So basically, if there is a missing debug information, what it's going to do is going to de-optimize that part of the code and git compile C++ while it's being debugged in order to recover information from the code. So that I think is pretty cool, because outside of the self family of languages and later, I haven't seen that done in native languages.
You know, they're catching up. This is 20 years, 25 years.
Speaking of C++, there was Ask Me Anything with Bjarne Strustrup the other day. Bjarne.
Oh yeah, that was good.
Not surprisingly, he admitted that the greatest language ever was C++.
Oh, I don't know.
No, I think he wasn't really comparing with other languages. I mean, someone asked him to compare Rust on Go, and he basically said that to do this honestly would be a full-time job, and he would have to spend entire time nothing but just doing language comparison experiments. I kind of see the point.
He was careful. He also said that every time he answers this question, he gets in trouble because his comments get taken. But then he added that, you know, they did what Rust did back in the 90s. He had this project that he did it in, and he just never committed it into the main branch or something, you know. So the whole pointer ownership concept.
I remember seeing pointer ownership concepts run around C++ for quite a while.
There was the Cyclone thing also. Was Cyclone. That was such a
that's not ringing a bell, but I remember there was some sort of pointer ownership, and smart pointers were intended to help with that. And then I don't know what happened to it. It was too complicated. And
2001, 2002, AT&T Labs. I should have known this. I follow AT&T. So that actually was a safe dialect of C. Rust was inspired by Cyclone. That I remember. Graydon was writing about this, and they added some very early linear ownership for C.
Yeah, linear types, linear ownership.
Right.
Yeah. I remember that going around.
There is also this language called ATS, but that's not really, I think, something that one would normally use. Not sure if anyone here was using ATS. It looks like this.
No, I don't recall this one.
So this one has very advanced type system, but it's, I would say, somewhat idiosyncratic. And to me, I think, for example, C++ template metaprogramming is an example of clean and readable code when I look at ATS, so it may be a little bit idiosyncratic.
I'd have to stare at that one a little bit to figure it out. C++ template programming always, I don't know, we used it at, maybe it's better now. I used it at Hotspot, but strictly for resizable array collections. Everything else out of the templates just turned into unreadable code over time, and so they got yanked one after another.
That's thankfully the trend is for it to die. I mean, they are mostly replacing this with the const expr, when you just add one keyword and then you just write regular C++ code and it works at compile time. So that I think that's much better, because a regular person can just follow what's going on.
Yeah. I think that's a much better idea. Oh my God, Heinz is going to show up here. What the hell?
All right, well, I will have to check out for now because there is a session I want to see. So
okay.
Thanks for that and have a good weekend.
Yeah, no problem. Hey, Heinz, okay, I got your floor, I think. It's not necessary to share a video of your floor, your ceiling. I'm trying to decide what angle I'm looking at.
One second. This one, there you go.
So, just so you know, these are getting recorded. It'll show up on Zoom an hour or two later.
Okay. Sorry I'm late. I just got the message. I was just doing some meetings by myself, or not by myself, off my own. Yeah,
it's all good. There's no agenda here, and it's just open mic. Except I ask if you're not talking to mute your mic.
Yeah, of course.
But feel free to chime in.
Awesome.
I think we just went around debugging optimized code, and patching x86 machine code, and portable patching and not portable patching, and patching anybody's code versus whatever. Oh, and a whole lot about model checking. And I'm looking at like somebody's just been to PLDI and they dumped a bunch of papers into the chat. So it was fun stuff. Da-da-da. Okay, so, you know, whatever. And then we just hit a break. So, you know, so now you have to. Yeah. I saw what was behind you. It's not going to work. Okay, anyone else have something new? Before we you know, invent new topics. So PLDI was pretty fun. Debugging optimized C++ code. That was the main fun new thing.
So I'm starting to look into the SSA stuff.
Oh, you got not okay, fine. You're not doing SSA all along?
Well, SSA is for the machine code production, correct?
No. C2 does SSA from bytecode to machine code and everything in between. It never comes out of SSA mode.
So it produces its IR using SSA?
Its IR is SSA.
I see.
It does not produce. The IR is SSA. Is only SSA and is SSA all the time. This is like always SSA all the time. If you've not done it, it makes life a hell of a lot easier. There's one IR, it is SSA form, and you do everything on it. And once you get your head wrapped around how that works, it's a hell of a lot easier than going back and forth and back and forth. And I've done plenty in all directions. And trust me on this one, please. SSA all the way, it's the way to go.
Yeah, there's not a lot of tutorials on it.
Well, the early papers, but then like Go write something that parses control flow free expressions and produces SSA. It's just a DAG rewriting. Parse an expression, a calculator expression, and you get a DAG out. Okay, that's your initial SSA form. Now add control flow by dealing with loops in the back edges one time while you're parsing. And that's it, you're an SSA form. Okay, live in SSA form for the rest of the compilation. I don't know. I found it straightforward. And once I taught people, they loved it. The Sea of Nodes is exactly SSA form, so the Graal folks picked it up. C2's been running SSA form only and always for 25 years. You know, the compiler team at Sun and then at Oracle grokked it straightforwardly. I'm happy to, you know, jump up and down and promote, but I'm sort of like there's no counter talking against me, so I might be biased here, but I have had some experience.
I'll know more once I understand what it is.
So have you seen enough to look at the phi functions? The only interesting thing about this is phi functions, and then you do the control flow game.
What they call phi nodes.
Phi nodes, phi, I don't care.
Phi.
Yeah, phi, phi. They represent merged data without actually any computation other than a merge. So, you know, here, I'll throw something in the chat here. Everyone, yeah, here, you know, right? So some predicate, and you get a 1 or a 2 for x. That turns into a phi function separate from the if. So as a control flow diamond, at the merge, you would have something that merges control flow, and you have something that merges data flow. The data flow is your phi. And it merges a 1 and a 2, and you declare the phi, the name x in the parser, but once you're out of the parser, you don't need the name x anymore. The x is just for, you know, parsing things. And, you know, people do this funny renaming games where they have some complicated whatever hell. Like, I never bothered with that shit. I just build it directly based on parsing expressions, and variable names get mapped directly to a node in a graph. One of the node types will be a phi. One of them will be a constant like 1 or 2, or an add operator. Function call operators and you know, if tests and everything else are all just nodes in a graph. I blend control flow in the Sea of Nodes blends control flow with data flow in SSA form for both, basically. And that makes life a lot simpler because you have just one one form to deal with. You don't have a control flow graph, and within that basic blocks, you get rid of the distinction. So you just have one thing, it's just a graph. Most of your optimizations are either graph rewrite rules or type flow analysis on a graph, type analysis on a graph, which is just a straightforward work list flow algorithm. Yeah, there you go. So SSA, yeah, let me pull this guy up here. The allocator has to come out of SSA to the name world. Yes, what it really does is it stays in SSA form. It also adds names. So the comment, I know exactly what comment you're talking about. So this is like stupid. This is me. This is like 20 years ago. I remember the code. Yeah, it's still in SSA form, but also it has names. So, and that's necessary because you have to flatten it to machine code in the very end. But I have useDef edges, def use edges, and everyone has a single def unless you start looking at the names, and then you'll see the same name repeat because that's your register number.
Makes sense. So that is just for loading these values. You just look at the register you need to load, right?
Register names are going to go out in the machine code. So there's an abstract interpretation model. The abstract interpretation model is SSA form on a graph, no registers ever. You start with bytecodes, which have their own register names, right? They have the bytecode stack locations and the actual registers.
Yeah, yeah.
Once you come into SSA form, those are all forgotten. There's an abstract interpretation model on the graph directly. When you go to machine code, you color sections of the graph with register numbers, and then you emit the machine code, and the machine will execute, obviously, its own state machine under the hood. It's got its own SSA form under the hood. That's x86 stuff. But the IR doesn't, you don't use the registers in the IR for any sort of abstract interpretation. They're there for code emission.
Yeah, okay, I see what you mean.
Well, and eventually you need to get out of SSA because your hardware, your registers are not SSA.
That's what I just said. I have also pick up register numbers. So I maintain the SSA invariant, which is I have a node and a graph everywhere. Every node is a unique SSA value, but now I color them with registers. And the registers obviously get reused over and over. So some nodes get the same register name. And that's what comes out of RAX on the x86 lingo, right? RBX, RCX, whatever.
Well, this is the point where it's not SSA anymore, because you reuse it,
right.
Reuse the same name for different values.
I would claim I'm in a little different mindset, but you're close. This is a state where it's ambiguous whether I'm at SSA or not. Because if I just strip my registers off, threw them away blindly, I am still in SSA form.
Oh, you have the SSA form backing it up, but if you're only looking at the assembly code, it's
yes,
like, no,
yes.
Yeah.
If you only look at the assembly code, it's registers and does all the register things. That's correct. There's an in-between stage between where I have no names. That's the standard SSA mentality. When I pick up the names for the registers at the end, I'm ambiguous. I have both SSA and registers, and I can pick and choose which view of the world by whether I look at the register names or not. And then, you know, obviously the machine code walker walks the graph and spits out instructions. It looks at the names, and that's the name it came out with. But even as I'm spitting out instructions, if I were just to strip off the names, I'm in SSA form. And that's what I'm talking about. I'm always SSA. Sometimes I'm also named, but I'm always SSA.
Yeah, so something I maybe can ask about, what I never really understood is if, right, you color your graph with registers, but if you run out of registers, I think I read the original Briggs-Kuyten paper, but you do something different here, and I never quite got it, so maybe you can.
Yeah, okay. So I do a Briggs-Kuyten colorer up until I spill. So there's a bunch of funny facts here about register allocation that are non-obvious that mean a whole lot if you get into CodeGen. If you're LLVM, you might notice this. So when I look at the program graph after it's all inlining and all optimizations and whatever done, and I see how many register colors it takes, typically it'll take dozens to hundreds of registers, depending on the coding style. So you will not color, just period, you just won't. So you go through and you split all the live ranges, and you put things in, when I split live ranges, the nature of it is I declare stack slots as another kind of a register which has particular hardware instructions that can access them, loads and stores, right? But they're just another register to be colored, other than you have to have a move to copy between a regular register and a stack register, which is a load or a store. Fine. So I split all the live ranges. Live ranges are allowed to color to whatever registers make sense for all the instructions that are involved in that live range. So in particular, I split live ranges in ways that will allow loads and stores to be used to cover the length of the live range. I def something way high, I use it way low, it's not used in the large section in the middle. I split them. The middle live range has no defs or uses, just at the endpoints. Therefore, it's entirely can be colored to a stack slot. So then I color again after the first round of splitting. At that point, I typically have one more, the average colorability is one more than the counter registers. So on a standard x86, you have 15 colorable registers. I have typically 16 neighbors in the live ranges. And it fails to color if you're large. If you're small, it'll color right then. If you're large, it will also still fail to color, and I'll do a more refined split and color again. And usually on the second pass, rarely on the third pass of splitting, it'll color. Some of the colors will be stack slots, and some will be regular registers. So it still breaks Chaitin colorer. The difference is where you put spills in. And I don't put spills in, which is maybe the real big difference. I put splits, and then I just recolor. Once I have a successful coloring, I then do a reverse pass where I maintain the invariant that I'm colorable always. But I look for places where I can make the colors adjacent, identical, and get rid of a copy. And that one's, just copy elimination and work sort of inside out for high frequency areas to low frequency areas to try and get, a few more copies out of the inner loops and such. And then there's very, very low frequency things that are all safe point branches that I'll take because it's all just compiler annotations. They all take any register, including stack slots. So they're all freely colorable. And so every time there's any chance of something getting pushed around, but it's also used in a safe point, the safe point puts no new constraint on where it can color. So all the dead code people were talking about, hey, how do you debug dead code, right? The usual story in Hotspot is it's spilled to the stack pretty early on. It's available as a stack colored location at every safe point, but it takes no machine registers. So the value is generated and stored. So the cost of generation of store is basically free on an x86, like really, really close to zero. So you had to generate the value and then it got stored, and then it never cost you anything ever again. So are you messing with the hotspot allocator?
Well, it was a while ago when I was doing the, whatchamacallit, I was generating the native call nodes and trying to pass in custom registers. And I ran into a couple of asserts in the register allocator because I didn't account for the extra register that's used for long and double values, right? Yeah. That takes up 2 stack slots as well on the JVM. So in C2, you get 2 basically nodes for those. And basically for the upper half, I was on 64-bit x86. So sorry?
On an x80, because that got cleaned out long time ago. Like there's 2 stack slots on the bytecodes, but the IR uses 64-bit ops, and so they get folded into 64-bit ops. When you go to the coloring side, if you're on a 64-bit capable x86, you use 64-bit registers. There's no high half, low half.
Yeah, you use 64-bit registers, but there's still a high half and a low half in the IR, as far as I can see.
And a low quarter and an almost low quarter.
Okay, that would be for the SIMD ops, SSE. Yeah, maybe. Yeah, the allocator is totally capable of handling register pairs. because the first x86 you had to do register pairs.
Yeah.
But then the x86s moved to 64-bit everywhere, and so you didn't need register pairs anymore, and they were way less efficient. So you did it with 64-bit ops. But now that you've said that, I'm trying to think if the allocator still knows about pairs of values that way, because the IR folded it into a 64-bit ops. There was no high, low. There are operators that will do high and low because that was the most efficient way to color for a very long time. When you got 16 full registers, 15 full registers on an x86, you no longer cared. When you had 7 registers in the stack pointer, and you had 64-bit registers, but there were 7 of them, you were still better off with pairs, stupidly. Not pairs, split pairs. Because most of the consumption of long values was done by big integer math, which was done by crypto, which always did things with high and low halves of ints anyhow, except for carry propagation, but they would shift left and shift right by 32, and mask and or mask by 32, and load and store, and sign extend, and blah, blah, blah. It was always basically int mask. You were way hell better off doing things with ints, pairs of ints, up until you got 16 registers on 64-bit registers. And then everything, as far as I know, everything flipped right before I left and hasn't flipped back, but I don't know. So maybe it does do stuff with pairs now. And then SIMD came along. SIMD was coming along when I left, and they were going to do pairs again. So maybe the pairs came right back.
So I know it does, right? I'm still using 64-bit registers, and that you see that in the generated code as well. But what happens if I'm trying to generate a call and I have a long as an argument, I get the real argument as one of the input edges, and then I have a fake upper half argument that I can mostly just ignore.
Are you doing, to Java calls? You're doing native code calls from the Java.
Yeah.
Oh, but you're probably doing a mapping game from the Java stack. Is that what's going on?
Java stack.
Yeah, if you're mapping from Java bytecodes to some sort of native call ABI, you will almost surely have to match the Java stack layout in the ABI call, which will, yes, have a blank value.
I'm not sure what you mean exactly. I'm just
okay. You're making a native call. You're doing some sort of native wrapper call, right?
Yeah. So this is just in the C2IR, in the ideal IR.
It's just in the IR. You should. Well, okay, fine. I did a rework of a bunch of that shit at Azul. Obviously, we had a custom hardware, but I just did it generically, and I cleaned up the native call interface a fair amount. I guess I don't know what Sun's doing. The native call interface ended up with Azul. I just did a short mapping from the ABI signature to the hardware signature as a piece of machine code that just swapped registers around. So it would handle the blanks that you got from a half stack. But I don't know what Sun's doing. So I recant. I don't know. You're right. I'm wrong.
Yeah, I'm not. The stack is not really involved. I don't think. It's just that the IR has these extra edges for upper halves of longs.
Right. When he goes to safe points, he totally has the upper half of longs because he has to map back to bytecodes. Most of the calls to native count also as a safe point because the native call does who knows what, may block. If you block, stack has to be crawled. If your stack has to be crawled, you have to have a mapping to the Java layout, which means you have to have something that declared a high half and a low half of long, even if the low half has all the bits and the high half is just a blank. So that might be was biting me too. I don't know.
Yeah, I think the thing was biting me is that I didn't account for the upper half, so I was just iterating over the all the arguments and assigning registers, and then the register allocator couldn't figure it out because the argument for the upper half had like an empty register mask.
Yeah, yeah. And then it blew up for no valid registers.
Yeah. Well, it didn't blow up. It actually said, it said I can do it after like 26 iterations.
Okay, fine. Yeah. It'd been nice to have it blow. Yeah. Okay, that could be asserted for. I know how to do that, but whatever. That's not my.
And I have to turn on a flag called wizard mode, so that was great.
That was like one of the most depressing set of things, of flags. There was this very, very early flag, wizard mode, which is basically the system's really simple. very, very trivial almost, and we need a little more debugging info. And then everyone piled in on wizard mode because there's a bunch of engineers. And it got too complicated, and wizard mode turned on every possible debugging printout on the planet. Okay, that didn't help. So then we all got our own debugging printout flags, and wizard mode hung on as long old school leftovers. But you know, the allocator came around while wizard mode is still the main debugging flag. Fine. Ah, what'd you miss? Oh, I don't know. We're talking about register allocation now. SSA form and register allocation.
All right, so did you solve the problem?
Obviously. I don't know. Jordan was talking about, you know, grief of using the C2 register allocator. And we were having, like, semantically, what is the register allocator saying when I say SSA all the time, and the register allocator is obviously putting register names down, what the hell does that mean? So that was the largest discussion. It means that you both have SSA form and also you have register names. And so it's ambiguous. And that was maybe the only thing that was not obvious there.
Interesting.
Yeah, so I want to spend some more time in the future sometime looking at the register allocator. I think looking at the history on GitHub, it's been worked about half a decade ago.
Yeah.
Or for the last time. What's that?
People got scared of touching it.
Yeah. Oh yeah, maybe.
It for a very long time, it did a very good job, fairly inexpensively. And in particular, and this is a crucial part of the Java performance story, it will fail when you run out of registers, and you always run out of registers. When you run out of registers, it will fail gracefully under load. So if you have hundreds of live register values, that will do a graceful job of spilling. And what by that mean is if you did not inline, then you took callee, caller, save, call overhead, and also you lost a lot of live ranges. So the prior allocators I worked at and C compilers I worked at before coming to Sun all had the problem that if you over inlined, the register allocator had too many live values and it spilled everything everywhere all the time. And you had a heavy cost for too much inlining that exceeded the value of the inlining by a fair amount. So there was a threshold curve where more inlining gave you more performance until the register allocator blew it, and then it just dropped off like a sharp knee in the curve. So you shall not hit the knee in the curve or you suck. So you backed way off from the peak. You backed down so you rarely would fall over and fail the register allocator. What I did at Sun was work very hard on an allocator such that the fail was graceful. So if you over inline, you peaked, but you never fell off. You just didn't get any better because there wasn't more to be had. The count of spills was roughly the same as the callee, caller, save overheads you would otherwise have. That meant that you could inline aggressively without paying a penalty in the register allocator. And that let Java inline way the hell more aggressively than the C compilers before it. Not talking about LLVM now, but at that era, Java was way more aggressive about inlining. And that turned into reliable performance wins. There was a good 5-year period where if I wanted to get another 5% performance gain across every possible Java program on average across the planet, I went to the register allocator first. The inlining second, register allocation first. So it's a nasty piece of work, but it does a really good job, and I can step you through more about what it does and why it does it. But the main tricks are simply keep splitting, sort of lightly at first and more aggressively to get a coloring out, damn it, and standard Briggs Chaitin coloring. You split high frequency around high frequency sections. So there's a whole frequency pass where I try to discover what I think are frequencies. And then there's a lot of inlining decisions people came up with. There are a lot of inlining cost models going around. One of the major costs, I was just talking about the major costs for over inlining is register allocation dying, and the hotspots was better at it than anyone else at that era. I don't know now. The other, of course, penalty was the inlining decisions were made before the optimizer kicked in. So you got basic class hierarchy analysis on the basic Java types, and that was, and frequencies from the counters, but you didn't get sharp analysis from the C2 optimizer to guide inlining decisions.
Yeah, those two I think are interesting because this post-inlining benefit part basically tries to see inlining as an enabler, right? Because that's what it is. Inlining enables a ton of other optimizations. And what's interesting in modeling inlining is actually right to quantify the cost of that. So what are the benefits of inlining in terms of the other optimizations that is going to enable further down the pipe?
The obvious thing here is that inlining should be done incrementally as the optimizer discovers things, as opposed to as pre-passed before the main optimizer. That was the hotspot sort of major fail. And the current way that shows up in the world is everyone who does large complicated iterators over complicated types, i.e. anyone doing funny languages, Scala, Python, JRuby, Clojure, all these guys. They all end up having complicated iterators, and the inner loop has a virtual call guaranteed or an interface call that did not get inlined. And therefore, all the good inlining optimizations around loops fail to happen in the common case for all these funny languages. You do this in Java, it works out pretty well. You can make it not happen in Java, but usually you get inlining in the hot inner loop, and then the inliner, the optimizer yanks all that shit out of the inner loop, and you run really fast. That's the major fail of the current inlining decision.
Interesting. Is there something that does this in inlining incrementally?
People have done it all the time. It's a common compiler strategy. I suspect the Graal guys do some amount of this incrementally. Certainly what I'm doing right now, I'm doing this incrementally.
Graal does incremental inlining. We in Falcon also do incremental inlining, and our cost-benefit model for inlining looks at the context of inlining, looks at the call side, and tries to use the facts which are available at the call side in order to estimate how many optimizations will happen after we inline this call side. So that's essentially what we're talking about.
That sounds interesting.
You have a very large, complicated inlining heuristic that works incrementally, which I think is absolutely the right thing to do. Yeah. And then the only question that comes around is, does a register allocator handle it when you overshoot the mark and you get too much? And that's generally speaking, that's a statistical thing to look at.
Yeah, the thing that got me interested in what I was seeing in generated code is it would spill all 15 or 16 general purpose registers to the stack and then reload all 15 into a different register. So I think maybe because of some code shifting around somewhere else, this introduced a subtle bug in the register allocator.
Yeah, it shouldn't do that. It'll do that if with low cost at safe point boundaries, where the cost of the code that's generated is essentially free because you only take it if you're also taking a safe point, which is far, far greater than the loads and storage. So the optimizer, in fact, the register allocator, in order to be more efficient, doesn't bother to clean up the copies heading into safe points. Yeah, so this is a known pessimism, if you will, because it's just not worth the time and energy in the compilation costs.
Yeah, this seemed to be. I think this was even in a hot inner strip bind.
If it's in the hot inner loop, then that's a bug. Absolutely. Yeah.
And there was nothing in between the two moves. It was just moving to the stack and reloading in a different set of registers. So
yeah, I gotcha. And in a loop. So that's a bug.
Yeah.
Yeah. Fine. Well, file it with somebody else.
How common is backtracking in situations like this? Say you have inlined a function, it looked like a good idea, but it has led to a worse register allocation later in later passes of the pipeline. Is there anyone that does backtracking when you then revert your decision to inline because it didn't pay off after all?
There are plenty of papers that talked about that when the concept of jitting came around new, like 1,000 people were talking about all these inlining heuristics and roll back and retry and whatever. C2 will, if you de-opt for some reason, C2 will track a bunch of shit and on the next go around typically do a little tighter job. but it won't unwind. It won't know that it was more expensive. Like you can't even tell if it's more expensive after the inlining and the register allocator is choked until you actually profile the code with like hardware perf counters.
Right. So what I think is then it would be rather too much of an overhead to do this in a compiler.
Yeah, right. To unwind and redo without serious cause is an overhead. That's
right.
compilation cost. That's not buying you anything. It's really easy to get stuck in infinite loops where you decompile and recompile and decompile and recompile over and over and over again. And we hit those 1,000 times at Sun.
Yeah, theoretically, you can analyze. You don't have to execute the code to see the characteristics after inlining. You can try to analyze, but still, you need to try, then optimize, and then roll back. And then the amount of decisions you need to try, I don't think that it's practical, at least in JIT compilation context.
I think you're being pretty optimistic about trying to run an x86 execution cost model over your generated code to try and figure out what it's doing. Because of spill cases and TLB misses and stack layout and iCache blowout and all kinds of shit, that cost model is going to be really difficult to be trustworthy.
Oh, I guess it's not to check for hardware-specific things. It's more like to see what kind of optimization is triggered on a higher level.
But that's interesting question, actually. Sorry, I'm interrupting. Continue.
So, and actually, there is a kind of variant of this. It's a variant of this inlining heuristic where you specialize the callee for the arguments. You propagate all the information you have at the call side. You run your optimizer on the specialized copy, and only after that you look at this copy and say, well, it looks good or not.
All right, GCC does it. That's the function cloning, basically. It's especially useful if you have some branch and you know something about data flow facts in that branch. Then you can inline specialized clones of that function.
The hotspot decision was to do that analysis cost the same as actually just inlining it, except that you could unwind. So the hotspot decision was, if I'm going to do that analysis, I'm going to inline it, and then I'll make sure the register allocator doesn't fuck up. So it didn't cost me anything to not unwind it.
Well, in our case, with LLVM, our problem was this kind of reasoning is it's just compile time. Yeah, we can inline and probably it won't be too bad in terms of performance, but it just will increase compile time significantly because it increases the amount of work for the rest of the optimizer. So that is why we try to be smarter in terms of what we choose to inline.
Yeah, okay, this is a compiler core technology game. This is where SSA as a graph pays off. It's guaranteed linear in the size of the graph and pretty damn cheap linear.
Something Arthur mentioned interested me for another reason. So Arthur, you mentioned this cost modeling, and I'm actually wondering, do you know something that would be applicable here beyond basic blocks? So the tools I know are things like Ayaka, LLVM MCA, Osaka, NanoBench, and PMEMVO, and UArchBench. So those are all microarchitectural cost models for Intel x86, AMD, and even ARM processors. But the problem is that all of those are, I think, within basic block. Is that right?
The major gain for inlining is to hoist out of loops. The reason to inline is rarely to get new types. That helps. Null checks are essentially free, but you can get rid of some. The major gain is you hoist out of loops.
Actually, we'll look for new types, and this gives us good hints that inlining is beneficial, especially if we can see that this new type in the callee would result in devirtualization or type check simplification, things like that. So this is a good indicator.
Right. So the type check itself is cheap, but usually you then cascade and get another inlining decision made, and then another, and eventually you bottom out the whole thing and you get a call out of the inner loop. That's the big gain. If you can bottom out the call chain because you can sharpen as you go, you win big. I'll totally agree, but I'm going to claim the win big is because it got pulled out of some loop.
Wait, but when we just have devirtualization happening in a hot loop, we don't hoist anything out of the loop. We just get rid of the indirect call on the hot path.
Yeah, get rid of the indirect call is a major thing. But getting rid of the inline and getting to let the call body leave the loop, the chunks of the body leave the loop, that's the major gain. Anytime you don't talk about a loop, you're talking about, hey, I got rid of 3 clock cycles to 1 or 10 clock cycles to 2, and on a fucking x86, no one cares. You have to multiply that by billions to get any numbers that mean anything. So it's always, you're looking to get it out of a loop.
Well, but it's not always that we have the loop in our compilation unit. It might be called from a loop.
You want, yeah, exactly. So you want to start from the loop and inline down in. You don't want to start further down in, right? It happens. It certainly happens at C2. There's no question. But the major decision made at C2 for inlining starts from look at places where the execution frequency takes a sharp jump between the caller and the callee. There's a loop here. Now that I have the sharp jump, I have a loop. Start from this loop body and inline the fuck out of it until I bottom it out.
Well, it's all fine, but we don't always have good profiles, so sometimes this...
You know, if you don't, you don't. But what I'm saying there, if you don't, then you've got a bunch of mushy numbers, and you're going to take a mushy value and shrink it by 10%. You're not overall looking typically to see big wins. I'll bet you if you got big wins out of tweaking your inline heuristics, that you could trace them all back to I cleaned out some shit in a loop somewhere. This is...
Yeah. So going back to the question about what kind of analysis there are. So the analysis we use for inline cost, and then actually a part of upstream LLVM, it's just called inline cost analysis. It does analysis of the whole callee, so it's not block specific, but it usually does not look into low-level architecture-specific aspects of it. Although we, for example, model the fact that our null checks are cheap and we don't care to take the cost into account, things like that. But in general, it's more high-level. But it can do the pruning of code paths. Let's say you are passing a constant into a function and you have a branch on this constant, and you can see that the big part of the function will be eliminated after inlining because you know the constant at the call side. So this analysis can do that.
Yep. That, you know, C2 makes the decision first to inline or not, and then if the constants are there, they obviously fold away, and the act of folding it makes the body of the function, like it's incrementally parsed, so it folds away the cheap way.
Well, the eventual result will be the same. It's just whether we will inline or not, and this is a hint that this is a good place to inline.
Yeah, I hear you. I don't know. I did a different way at C2. It seemed to work out well for the reasons that the act of doing the analysis exceeded the gain for not bothering inline once you did the analysis. That's all.
And as you mentioned that we see this more hard inlining cases on these new languages. And I think in general, newer idioms, even in Java code, they produce more hard cases for inlining. And what works like on canonical Java code like 10, 15, 20 years ago, well, now we have different canonical Java code. We have harder cases and we need to do smarter analysis around this stuff.
You know, my experience says it's you need to pull the hot virtual calls out of the inner loop. Yeah. And that means you need a clone at the loop boundary, typically, to get the hot inner loop guy to have a known constant time type.
Yeah, definitely agree that if we care about some code, it is in a loop, and otherwise, like it is in a loop in some way, whether in this compilation unit or somebody's calling it, like otherwise it won't be hot.
Right. So I'm just saying start from the loop and work your way forward as opposed to the other way around. Although having said that, totally C2 gets handed shit that's, you know, not in an obvious loop boundary anyhow, because that just happens. Yeah, that's fine.
Yeah, often all these smartness, it's about robustness of optimization, because like you would every once in a while get some case where this simple thing doesn't work nicely and it's tricked. So you have to do
heroic analysis and efforts in order to crack this hard case.
There's definitely a thing there where it needs to be robust across a large body of people, even if you don't get the ultimate speed out for some folks. If you have any potholes, you'll get plenty of screaming and complaints, and people can't trust that the optimization of the performance is reliable. So yeah, robust is more important. And that turns into how to say whether your technique or what I'm doing are better or worse, turns into a statistical analysis game over a large body of codes, which we don't have any, so.
Yep.
That's what it is. Well, we have a little break in the conversation. Does somebody want to chime in here? So I'm gonna declare victory this week. This is a fun one, and like 1,000 papers I want to go back and stare at here. Yeah, combinatorial racial allocation instruction scheduling. It was another fun thing I did many years ago. Yeah. Well, I hope to see people again next week. This was good stuff. And then, Cameron, I'm gonna have to beat on you on SSA form here.
Well, I wish I could, if you got a minute, I can kind of show you our approach, and I'd love to see how it differs, because I'm still trying.
Yeah, I was hitting a break in conversation and saying it's 11:20, but I don't have a necessary thing here where we're chasing cats down.
Can I share a screen?
Yeah, fine. I'll probably have to enable.
Yeah.
See if you can share while I hit the button here.
Not yet.
Yeah, here we go. Okay, try now.
Et voila.
Okay, I didn't get it yet though, so.
It's coming.
Oh, boom. Okay.
Yeah. So in the example you gave with the ternary and the assignment,
yeah.
Like, so this is the ternary generation. So, like for these nodes that you're talking about in SSA, they just represent instructions, right, in the IR?
They represent, yes, every instruction that you would emit in machine code is a node. Also, they'll represent control flow points, merge points, which do not emit any code.
Is that kind of like a label? So a label, we use a zero length op called a label to represent
branch target.
Branch targets.
Yeah. So that's very close to what I do for control flow, but it's missing some key thing. The key thing is at a merge point, I call it a region node because of Ronnie Ottenstein Warren region nodes, but it's basically control flow merge. It has two inputs, it has a left and a right. Now, it actually has in inputs because it is an in-way merge, but the standard balanced control flow you get out of a high-level language gives you two, but the optimizer might get many. So start with two. You got a left and a right and merge point. I have an if at the top, which takes control flow and a data value and splits it into two control flow edges. And now I said control flow edges. What does that mean? It means I have data values flow on data edges, control flow values flow on control flow edges. And there's control flow, and it's because I mix my graphs to include data and control. So I have one flat graph for them both, and they don't have basic blocks. So I get a graph for the IR, and I can share back at you if you want a visual representation of this, because I have the right papers to show sort of simple IR. Would that make more sense here? Are you done with this thing before I kill you?
Well, I wasn't sure what questions you would ask, so I hauled up.
No, I see where you're at, kind of, and there's another go around we'll come to. Like, but let me share first, and we can come back to here.
Sure.
If it makes sense.
Absolutely.
Okay, once you stop share.
Sure.
Okay, and now let me go find mine and do.
And this one came out dramatically different because I designed this instruction set as a register-based instruction set, as opposed to stack machine model that I used in the Java compiler.
Right, and I'm using always graphs. I'm trying to figure out where. Here we go. This is a IR95. I'm not kidding. And this is what C2 is based on. And let me figure out how to share here. You probably don't want to see. Here we go. How about this? Let me see. Let me know if this shows up here.
Yep. Simple
Okay.
graph.
So boring. So here's a graph with BC and add, and that's just, hey, piece of data flow. And here's a mentioning control flow with regions and some output and input edges. Here's a little more complicated where I've got control flow and a fee. And you'll see block 1 and block 2 merge at a region, which takes 2 inputs. That was your label, but with 2 edges, a left and a right. And then there's a fee, which has 2 values for X getting merged. I drop all the X's and the names when I'm done, right? And then there's an if right underneath it, which is showing a control value on one side, a predicate on the other, 2 outputs, true and a false. Let me go down here. Here's memory, which is just a value. Memory is just a straight up value. So pointers are values, memories are values, controls are values. Okay, here's a little loop. So the little loop says, hey, add 1, test and branch. So there's a start control, there's an end control, which is not up here. There's a region, which is taking the back edge. There's a fee with an add and a 1. There's a test of some kind. To make my graph more efficient, I don't have edges as structures in the design. Edges are literally only a pointer. So if I want to label an edge, I have to label a pointer. Can't do that conveniently. So I add a node, which is basically an edge label called a projection. So an if produces 2 values out, a left control and a right control, produces a tuple. And I have a projection slice 1 piece of the tuple out. I do that for every value, everybody who produces more than 1 value out. So calls produce out a memory state and a return value and a control flow, typically some sort of exceptional control flow as well, produces a bunch of values out. And the projections to slice them all. And there's some discussion of implementation I won't get to. I'm gonna find a bigger picture here. No, where's my big picture? Oh, this guy didn't have the damn big picture, damn it. I missed, I have a better picture somewhere. All right, we'll go back to the easy picture. So there's implementation for efficiency going on down below. But this is what I'm talking about, for instance, graph. That the blue edges on the region are actually not in there at all. And that's because it's IR95. Let me go.
See, we don't use a graph per se. We just actually emit linearly. So it's a linked list for all practical purposes, or an array, whichever way you want to think about it.
Yeah, okay. Here's the more complicated guy doing GVN GCM. Yeah, so there's a better starting point here. This is good enough. So here I have some little code here. The top left has got a sort of classic compiler paper C-like fake language. There's a graph on the right where I've put a basic block around, but the actual implementation just has regions where the control flow for the basic block goes. And then I have adds and fees and greater thans and multiplies and tests and branches, shit like that. They're all nodes in a graph. So there's one layer graph. The shadow boxes for putting basic blocks around are not actually present. They're there for presentation purposes because I have to do global code motion. So the goal of this is to decide where I have, when I come out of SSA form, I have to do basic block placement. When I'm in the sea of nodes, I lose my basic blocks, and it lets me optimize sort of much more freely without worrying about where an instruction lands relative to anyone else except via use-step edges, strictly use-step edges. So it's all graph rewrite rules where I look at use-step edges to do 99% of the optimization. Yeah, 50% of the optimization. The other 50% is I do loop things. And that goes to placement, getting things out of loops, pushing them either up or down. And then all the dependence edges follow when you push them up or down. So there's an algo to flatten the damn thing into a control flow graph from a sea of nodes. But the actual optimizations, the core optimization work, including all the type flow analysis, all the things you'd use to decide I'm going to inline again, so the incremental inlining based on presence of constants or known subtypes, null checks or not null checks, that's all done on the graph-IR, all done with graph rewrite rules, with a simple work list algorithm, all guaranteed linear time, all guaranteed short, fast linear time. And this is what the core C2 optimizer does. I emit this from reading Java bytecodes directly. I, in fact, incrementally optimize it while I'm reading bytecodes, because you can incrementally optimize it while you're reading bytecodes. That cuts the size of the generated IR from the bytecode generators is stupid. I just produce the obvious, completely safe translation every time, of which, 90% of the time it's canonical easy form that folds a lot of shit away, like all the array math for.
Is this paper online?
It has been in the past. I can certainly throw a link out on Twitter.
Perfect.
I'll throw the links out. I think this one hit a conference. This one didn't directly, although I thought it got published. This ACM copyright, SIG Plan 95, probably came out with the IR95 one. It was a co-located. This is the core IR technology that's used in C2.
I have this paper locally as well, so it should be online.
Yeah. So it came out in IR90 in PLDI 95, but I can throw the Twitter link out.
Perfect. All right, I will take a look through that.
Okay, stop share, boom. Yeah, fine. It's like I said, once you get your head wrapped around what it does, because you have to think in a graph or program semantics, it's way the hell easier to do all the follow-on optimizations. There are a bunch of people who sort of like, when I started doing this, there were a handful of folks who ever tried it. And for the next decade, very few people actually did it, but most of the planet was using it in C2 without realizing it. And slowly the compiler community started to recognize what the hell's going on. Now that's separate from SSA. People would jump on SSA, but they went in and out of SSA form. And I just said, no, stay in SSA all the time and do everything on graphs, and becomes a graph rewrite rule. And suddenly, holy shit, it's fast, it's easy to do. It becomes super it's straightforward to go do all kinds of optimizations that are not the loop ones. All the flow things go, and all the incremental small things just go super easy.
Just to add a note here, I think SSA and graph representation, they are somewhat orthogonal. You can have SSA not having it represented as C of nodes or as a graph.
They're orthogonal. I totally agree. I'm doing it combined because there's a huge synergy there. So if you read the paper, there's an implementation of how to do it, and it's what C2 does, and it's just a straightforward thing. You have a opcode, you have the set of pointers to use steps. And for incremental efficiency on the big work list algorithm, you have the def use edges too. And that's like it, and that's the entire IR. And from there, you have a bunch of code that works on graph pattern match to decide I have the right pattern and mutate the graph. And then scaling that across a team of a dozen guys requires a bunch of invariants and various kinds of checks that you do to make writing the graph rewrite rule straightforward and have the right properties. So you have to have a monotonicity property on all these things, or you endlessly unroll, or you endlessly do X or Y. So there's a bunch of canonicalization, but they're all like obvious things to think about. Hey, if I do this transformation, I'll get one less of item X in the graph. And so that's an incremental monotonic improvement, right? I guess C2 eventually picked up an incremental dominator tree to do more, null check, cast check removals. I'm trying to think of what other things. When you came out of SSA, you pick up basic blocks. All that really meant is I assigned node to a region node, and that was your basic block. I picked up anti-dependencies to force loads and stores to order right, and then I hit the register allocator. We picked up register name, so you pick up little bits of trash on the way out. Coming in, you filter down to have almost nothing except the program semantics. You do optimizations on it, including all.
I guess the other question is now with tool sets like LLVM, how much of this can you leave up to the back end?
Well, the reason I did it with C2, C2 is hugely faster than LLVM because of the games it's doing here. at the time when I did it, LLVM wasn't an option,
Right.
nor was GCC, right? So nowadays, LLVM is like a reasonable code generator and handles all the Java. It was always a reasonable code generator. It handles all the Java shit, garbage collection like that it didn't handle back in the day. But it's not as fast as C2 by a fair
5 to
amount.
10x in our case.
How much?
5 to 10x slower than
5
C2
to 10x slower than C2. Yeah. Yeah. So that's the difference. For roughly comparable in performance games. I think you guys are doing other things with it too. But performance on C2 has been pretty damn good.
We actually had a stripped down version of Falcon where we tried to stay at the same performance level as C2, and I think we managed to get down to 2 to 3x slower than C2. So the version which is 5 to 10x slower, well, we show better performance on on big variety of loads compared to Zinc C2. But yeah, that's the price we pay with LLVM.
Yeah. Okay.
And I think 2x going lower than 2x going to be hard. So having 2 to 3x, it was manageable, but going faster than 2x slower than C2, yeah, it's.
Do you know where the difference comes from?
Well, I think there's a lot of things, and as Cliff said, that there is a fundamental difference in the IR in the way the optimizer is organized. So when C2 does this incremental rewrites on the graph representation, in LLVM there's, I would say the general philosophy is to do small incremental transforms and then do big things by chaining them together. This is good when you want to test, debug, understand what's going on, but it's costly in terms of compile time. It's easier to understand where things went wrong when you have 5 different simple transforms. You look at the visual and you see, okay, that makes sense, that makes sense, that makes sense. When you have some smart analysis which did several different things at one shot and then produced some result, it's hard to say what went wrong and whether this thing is correct or not. But this is fast.
What C2 does is not really what you just said. It does a lot of tiny transforms. The transforms are each individually tiny and locally obviously correct, and it does a lot of them. So I chain together thousands to hundreds of thousands of tiny transforms.
Well, maybe my impression then comes from various analysis you try to do in the lattice, and you compute many different facts at the same time.
Every single node computes its own fact about what it has. Yeah. That's a fact per node and a node per fact, if you like. The lattice is just a convenient way to describe a set of things that can be described by the program.
Well, I think even one of the papers which you showed today, the one which is global value number and something else, it is about combining two things in one analysis.
No, that's my PhD thesis. That's a little different one. Yeah, the PhD thesis is combining a whole lot of optimizations globally. So separate out. There's the graph version of things supports a incremental, pessimistically always correct version where you do tiny transformations by the bazillions, and the graph incrementally shrinks and gets tighter and more efficient as a program semantics. But at any point you can stop and it will be correct. So that one has this nice property that it's always incrementally correct. Then you stop and you do global. I'll throw the link on Twitter. Look for the link on Twitter. You stop and you do global transformations. So for instance, you do global constant propagation, very classic global constant propagation algorithm, where you stop and you say every type starts at some top value, they all fall down a lattice until it stabilizes, and then I have my constant propagation done. That one's not correct until it stabilizes. Once it stabilizes, then you do the big sweep and say I have a bunch of constants I discovered, and I'll replace computation with constant. The thing that the thing I did in the GCM whatever was combine because I have a single combined graph, I do conditional constant propagation. It's a very old technology. It has nothing to do with SSA. I just do it on the graph, and it looks exactly like constant propagation, but with control flow and data values at the same time. There's no other difference than that. It's just standard constant propagation, except now I include control as one of the values. And then the PhD I did was, hey, I could also combine this with other shit. But this is all in this context of stop the world, do a global analysis that has to fall incrementally until it stabilizes. Once it stabilizes, the new stable point is correct and presumably improved on something, and then you take advantage of the new data. But the larger majority of optimizations are all done by this incremental pessimistic only approach where at any point in time you can stop it and it's always correct. In particular, I put a counter loop on doing the transformations. Like I pull them off the work list, do one after another. And if I have one in error, but I don't know which one it is, I have a counter and I can fucking binary search it. Because I can just binary search up to this point, stop, done, this is correct, go execute. Didn't work, it worked, I don't know, add or divide my number in half and go again. So it's entirely incrementally correct as a transformation.
Yes. Sounds like my impression is based on this global analysis and transforms, not on this rewrites.
The rewrites do the majority optimization. The global analysis was my PhD, which was a fun piece of math that I got, my advisor to sign off for, but it's not implemented in C2.
Oh.
Global code motion is implemented in C2. That also showed up my PhD, but that wasn't the thing that I got signed off on. That was a separate piece of work. I got signed off on the theory behind what it takes to combine global analyses in a way that's provably superior to running any individual global analysis back to back to back an infinite number of times. That's what I got signed off on. What C2 does is it does a global analysis that's combined control flow and constant prop called conditional constant propagation, but that was not unique at the time I did it or at the time I did my PhD, and I didn't get anything signed off on. That was just a good implementation strategy. And that is a global pass. You'll hardly notice it in the compile times or in the improvement it does. It finds a few extra constants that you don't find from the pessimistic one, but never very many. I do the pessimistic thing while I'm parsing. When I'm done parsing, I add the reverse edges. I finish doing pessimistic things. That's your 90% case right there. I get a few more for the global constant propagation because it was a good thing to have. And then everything else is like loop ops and register allocation. And the only thing I'm really missing out of there is incremental analysis after the pessimistic done to do inlining in the right way. So the inlining heuristics always get kind of aggressive, but still miss the mark sometimes because I don't have enough information. So are you drowning in data now, Cameron? Is that what you wanted to hear?
Absolutely, always.
Okay.
I wouldn't have it any other way. I do have to run though, but
okay.
Thanks, Cliff.
I'm going to call it here. We can pick up this conversation again next week, Arthur. I think this is a fun one because this is the thing that I'm really proud about, and it really made a difference, and it's not well understood by a lot of folks. So I'd be happy to clarify or brag, whichever comes first. Next week. Okay, guys. Bye-bye.
Bye.